Hello, everybody. Thank you so much for joining us today. We are so excited to get into this kinetics experiment with a forensic twist. As people filter into the room, now is a perfect time to have you navigate to the bottom of your Zoom window. At the bottom of your Zoom window there, you'll see what looks like a little chat bubble. If you click that chat bubble, you'll be able to see the webinar chat. This is where you can send all of your questions today. We're going to be keeping an eye on that chat. So as you have questions throughout the presentation, please feel free to pop a question in there, and we'd be happy to help. Now, we don't want to look like we're talking to ourselves, so please make sure that in that little chat bubble, you click that to and set your to everyone. That way, when we're answering your questions, people know what the questions were, and we're not just formulating things out of the air. To go ahead and practice that, please navigate to the chat bubble. Make sure you set it to set the to everyone. And go ahead and let us know what your favorite chemistry pun is. I don't know if that's too big of a pun. We're just talking
Oh,
about Nüs's shirt, so I don't know if that's too tall an order, but I love a pun, so I would love to hear what
ah,
you all are working with.
oh, let's see, man. You put me on
On the
favorite
spot.
chemistry fun.
Oh, Rose has a good one. Be like a proton, stay positive.
I like that one.
Yay!
The element of confusion.
Yep. Nah, bro. I like that one. I
That's a good
like
one.
that one.
Good.
Yeah.
Hoke and
Oh my gosh,
Molly. I
Amy,
love
that's a
it.
good one.
That was my
I would
hand
tell you
there.
my favorite
All the
pun, but
good
all the good
puns are
ones are
gone.
gone.
I don't think so. Let me throw that one in there.
That's awesome. Thank you all.
Like it.
That's a
Good.
fun way to start a Thursday, so we
hmm
appreciate that. Oh,
Oh, I can't type.
I don't think
I
so.
don't think so. All right.
Coppers and let's see what else.
Argon, the pirate's favorite element. That's
Oh God.
awesome. All right, well, to make the most of our time together today, and please feel free to keep dropping those puns in, I will be watching the chat. I do have some housekeeping items to get into. If we can pop to the next slide, Noose.
Oh, sorry. I was watching the puns. I'm having
No worries, I get it. All right, so you will get a recording of today's webinar. It will be live on our website in about 3 to 5 business days. You'll receive an email with a recording link, so keep an eye on your inbox and we'll make sure we get that to you. You'll also get a resources folder with a link to today's presentation. I'm going to drop that link into the chat as soon as I'm done talking. And as I mentioned before, we want to answer your questions today. If you see anything pop up and you want to know more, go ahead and drop it in the chat and we'll try to get you an answer. If we happen to miss your question, or if it's something that really requires more of a conversation, please send it to chemistry@vernier.com and one of these two lovely folks will help you out. That being said, let's go ahead and jump into our webinar. Thank you all again for joining us.
Hi guys. My name's Nüs Hisim. I taught chemistry and physics in Maryland for 34 years. Been at Vernier for almost 10 years now. And I've known David Vernier since nearly the beginning. So I've been using a lot of his equipment, mostly in chemistry education, but sometimes in physics education as well. Melissa, you want to say a couple things about yourself?
Yeah. Hi, everyone. I'm Melissa. I'm the other chemist. So if you call the office or email chemistry you're either getting me or Noose answering your questions. Yeah, and I will be answering all your questions in chat today, so feel free to throw those out there as they come up. I'm very comfortable interrupting Noose when it's appropriate to get those questions answered, or if you want to see something again, or so please use the chat window. I will be monitoring it, and Noose is gonna drive, so take it away.
All right, here we go. What well, let me kind of fill this in just a little bit before I talk about these books. What drove this webinar today was requests for kinetics. a lot of people asked about kinetics back in October during Avogadro, during the 23rd, or close to Mole Day. We did some electrochemistry stuff, and we love to customize these things for our users, our teachers. So make sure that if you want to see us do something, please, in that form at the end that you're going to get at the end, yeah, throw some stuff in there. Hey, show me how to do more electrochem, or show me how to do something with equilibrium, or show me, we would love to do that. Um, the other thing that kind of motivated me when I came to Vernier is, the student in my class is, when am I ever going to need this? And so I wrote, well, Melissa and Elaine and I worked on food chemistry when I first got here. Lots of cool experiments that use food. And at NSTA, we're going to do one in Philadelphia in a couple months. And then my passion sort of was forensics, because NCIS and all those bones and all those shows, the kids are all about them, right? So the forensic chemistry experiments is another one that we just finished that like a year ago or something like that. And the other thing that I did that was different from what they were doing here at the office for a million years, I mean, not that long, but like 40 years, was I correlated every experiment to a topic in chemistry. So if you're teaching acids and bases, or you're teaching electromagnetic spectrum or whatever, then you're going to find experiments to match those topics. Originally wrote these for graphical analysis. We are on the cusp of releasing the LabQuest versions of these for those of you that are using LabQuest. And so yeah, so that was kind of the motivation for this. The other thing that Melissa and I have started working on whenever we can, this is like the most fun thing, is trying to use more green chemistry considerations when we write the experiments. This one blew me away, folks. Crystal violet. Read the SDS, download the SDS for Crystal Violet. That one in the back, think I got that one from, I think I got it from Thermo Fisher. I think that's where that originally came from. And then the Flynn one, for the food dye. Of course, there's no hazard for food dye that they identify. I mean, I got some blue on my fingers today. But if you look at Crystal Violet, hmm, should we be using Crystal Violet? I mean, it's kind of nasty. And the question is, what are you trying to teach, right? You're going to see in a minute or a few minutes that you can use blue food dye and teach the same concept, and it's, pour it down the drain. Melissa pointed out, I didn't realize it, we're going to use bleach, but she pointed out, you can also do it with peroxide. It's a little more challenging because you got to control the pH, but it's not a big deal. So yeah, so there's some alternatives. And with green chem, we're trying to do that. We've got some electrochem stuff. We've got, what else do we do? Oh, we did, Melissa's working on AP Chem #1. What is that?
Sports
Sport.
drink.
Yeah, thank you.
Yeah, we got that one up
That's in
there.
there.
Got some titrations in there.
We've got two titrations we've done, and we did a webinar on those actually. So anyway, let's get to the meat and potatoes. Especially AP Chem. I taught AP Chem for 25 years. I read for 1 year. That for me was plenty. Okay, I'm just saying. I know you guys that like to read every year. Knock yourselves out. Thank you very much. I did it for 1 year. It was in Daytona, Florida, so that helped a little bit. But look at that. Even last year, where's last year's? I think this one is, yeah, 2024. This is last year's. And here's the sad thing. When I was reading these, so often, more often than you hope, these would be blank. The kids would not put anything down. Or they'd say, my teacher got pregnant and we never got to that concept. Or that was chapter 19 and we just didn't get to it. And it's like, really? Or the other thing is, I'll tell you right now, when I first started teaching, thank God for chemistry with Vernier, because last time I looked at some of these topics was first year college, first year chemistry. And so, boy, was it helpful. These Vernier experiments, now, well thought out, well tested. And so now, can you do this experiment on a cheaper device? Yeah. Back in 2023, we did this on a colorimeter. And so you're going to get a link to all this junk I'm showing you, including this those links that are on there. So you can go and you can see the recording or the data files, all that I'll share with you. Today we're going to do it on a SpectraViz. Boy, those are scary hands. Those are my hands over there. Melissa did the one on the left. I did the one on the right. You can see how much nicer hers is. And we're going to also share the files. So you'll get all the files that I'm working with today. What are we going to do? Lambda max, you saw there was one question on, why do you choose this wavelength, or how do you decide what wavelength to do? Determine the order of the reaction. And how many questions, Melissa? Can you do calculations in spectral analysis? Do you have to export to Excel, or can you export to Excel? Yes, the answers are yes, yes, yes. And then the other one is, can you convert absorbance to concentration in the software? Absolutely. And I shared this file in the shared documents with you as well. And so this one, it's a whole Beer's law discussion, right? So if you want to know why do we recommend use solutions that absorb between zero point 0.1 and 1, this talks about that as well. If you look at this graph, there's percent T against absorbance, and you can kind of look at that. We're going to use this today very quickly because of time. Nüs is talking too much. But you get that, okay? How do you write the expression? In terms of concentration, not absorbance. You can write it in terms of absorbance. Do your students know that absorbance is directly proportional to concentration? Maybe, maybe not. And then we'll talk a little bit about this thing about half-life and why you would do that. It's fun. It's real. Kids have heard of half-life, but what is it? Okay, and so left is what it looks like on a colorimeter to find lambda max. Right is what it looks like on a SpectraViz to find lambda max. But you can do it on a colorimeter if you have Graphical Analysis Pro. You can even make bars. I think the bars are nice because it's a nice visual. But if you didn't have Pro, if you had the free version without Pro, you would just have dots. I mean, if you wanted, you could connect them. That helps a little bit. The spectral analysis has no pro version. It's free and it's completely free. So anyway, something to know about. So here's every experiment in the forensics book has a scenario. I'm not going to read this, but the crux of it is, you know how you're told at the airport, don't leave anything lying around because it'll get seized or whatever. So someone left a backpack. Well, sure enough, they found a bomb in the backpack. That's the story. I wrote these. They're a little cheesy, but police disabled the bomb. There's a manifesto in there that says that the bomb was supposed to detonate at the half-life of the reaction. What the heck is that? If you're a detective, okay, so part of your job as a crime scene tech is to determine a half-life, but also to explain it to a policeman or in court. I had actually had some CSIs come to my classroom, and there's a whole set of classes they have to take in college for testifying. How do you do it right? So it's actually part of their job. Two CSIs came in my classroom. They were both females. I kind of like that. I like the idea of the kids seeing that, it's not a gender thing. So here's what we're going to use for the experiment. And it's all in front of me here, and you're going to see. I'm going to show you why the graduated cylinders are fine, but you'll see one of my favorite things to substitute for that. A real dark blue solution, and we'll talk more about that. And then we'll get into converting, right? And see, okay, so let's do the experiment, and then we'll get into some of that other stuff. So I'm a Mac guy, so I got to think twice about how I'm doing this. There we go. So here's all the stuff. Okay, I made up a real dark blue solution, and there's a good reason for that, and you'll see why in a second. Um, and so let's take a look at it and see what you have to do. So in the experiment, what the kids have to do is, in this one, I wrote two experiments, one for colorimeter, one for SpectraViz, and you'll get both of them. And so the SpectraViz, the GoDirect SpectraViz, can connect, all our GoDirect sensors can connect two ways. They can connect by Bluetooth wireless, or they all come with a USB cable and they can connect directly with a USB cable. Now on a Chromebook or a computer, the university, what is it? Purdue University's chemistry department is all iPads. So they only got one option, and that's Bluetooth. So what I'm going to do on the Spectraviz to get it to connect by Bluetooth, I'm going to push a little button on the front. There's a battery in it that you have to charge up. So the little flashing LED means that it's transmitting a Bluetooth signal. I'm using the free, easy to use um, version of spectral analysis that runs in the Chrome browser. And so you simply just type in spectral analysis. Here, I'll make it do it again. And it just comes up. Now, if you're on a Windows computer, I think it works in Edge, but I'm a Mac guy, so I don't know that. So down here it says connect a device. So I'm going to do that. Which way do you want to connect? I'm going to connect by wireless. And there it is. And so the Spectraviz pops up. This number is the one that's on my Spectraviz. So I click on that and I click on pair. And if you know anything about Bluetooth, throw the salt and pray to the gods. Bluetooth can be troublesome, sometimes, especially on Chromebooks. So be aware of that. And so look, it's ready to go. It's ready to do an experiment. So what I'm going to do is I'm going to do if you click on absorbance, we actually built in here a full spectrum option, which you could use for what I'm about to do, but you'll see in a second, you don't necessarily have to. A Beer's law, so an events with entry option, and a kinetics, a time-based option. And that's the one we're going to do. And so I'm going to go ahead and pick that. And what's going to happen is it's going to put me in, I should have done this a minute ago. It's going to put me in the calibration mode. So while it's warming up, I'm going to go ahead and get my solution ready. If you're not familiar with our colorimeters and spectrometers, they come with 15 plastic cuvettes. This device can read from 380 nanometers to 950, I believe, nanometers. It can peek into the infrared. You have to use a fiber to be able to do things. Knew that, which, by the way, I wrote in the forensics book. I wrote an experiment. I wrote a flame test experiment. But it'll peek down into the UV, but that's not too great. And so it comes with these plastic cuvettes, which are totally adequate for this. But don't try to use these with one of our UV vis spectrometers because you'll get crappy data. And that's a very common, why does my data look so bad? And it's like, are you using quartz cuvettes or are you using the plastic ones? And then we get a little silence on the phone. And it's like, oh, yeah, okay. So I'm getting the blank ready. I'm cleaning the clear sides, and I'll put 3/4. The light path is at the bottom of the chamber, so I want to make sure I've got, like, I don't know, 3/4 of a test tube of water. And so clean that up a little bit, line it up so the light path is left to right on these devices. So I want to make sure that's sitting in the light path, and it says, oh, look at that. So what's nice with the software now is we can actually put less instructions in the experiment and say, click on, when it says calibrate, follow the instructions on the screen. It's really, the software guys, Melissa's big into this. They really made a nice piece of software. And now it's telling you, okay, what do you want to do? So I'm going to take out the blank, and I'm going to create a cuvette so I can measure lambda max. By the way, look over here. Okay, multiple wavelengths. We'll talk about that in a second, but let me get my cuvette ready. So this stuff, I made it up in the lab this afternoon. It measures over 1.5. Spectral analysis maxes out at around 1.5. And so if I put that in there, I'm going to get kind of a flat graph. So what it says in the experiment is dilute the solution so you don't get a flat graph. So I'm going to take just a small amount of this blue food dye that I created earlier. I don't need that much. I need to leave room for some water. There we go. And then I'm going to do is add some water. And it's not critical at this point that I'm super, super, super careful because I'm just looking for lambda max. So, I put a cap on there. This is food color. I can use my finger. Maybe not good hygiene. So for your students, put the cap on there. All right. So now look at the graph. Okay. Oh, baby, there's a peak, right? Why wouldn't you use the peak? Well, you might be teaching your kids about looking at the shoulders on a colorimeter. The high red LED is 635 nanometers, so you'd be on a shoulder. But yeah, you would pick that. You can also type in your own value if you want. So if you don't want to, just manually do it, you can just say, you might tell your students. I think it's better for them to observe it. Now here, why do you want to do multiple? Well, green food color from the grocery store is actually blue and yellow. Maybe for some reason you want to study both of those. So you can actually choose more than one peak if you want to do that. Okay. It is kind of amusing. For this experiment, though, I'll warn you, yellow food dye does not react, it'll react with bleach, but it's not the same concentration. So you may need to make some adjustments if you're thinking about doing that. So anyway, I'm going to say done. Notice now I've got a little mini graph up here of the whole spectrum, and then it says absorbance. Let me make that bigger so you guys can see it. There's an option there in both of the softwares to kind of make them a little larger for demos and if you're teaching your kids. Absorbance at 628, time, that's a live reading right there. So we're almost ready to go. Now I need to set up the actual experiment. So I'm going to take that cuvette and actually good spectroscopy hygiene. I should use the same cuvette that I calibrated with. So I'm going to go ahead and knock that out. Okay, get that ready. Now, in the experiment, it says 10 milliliters of blue food color and 10 milliliters of bleach. The bleach, let me get the experiment started so it's, cooking along. So it's going to take a minute or two. And then we'll talk about the bleach and the food dye. So what I'm going to do, I really love doing it this way, by the way, and you'll see why in just a second. So I'll put the food dye into the beaker. And then this is the part where you sort of kind of have to be ready. But I'm going to tell you a trick I did. And Jack Randall, the guy that wrote the advanced chemistry book, he's the one that told me about this. And so I'm going to take the bleach, which is diluted, by the way. It's diluted. And we'll talk about that in a sec. And we're going to put that in. And I'm going to change the experiment because this part gives you the impression that you have to do it real fast. And I'll tell you why I don't necessarily have to. So I'm going to put the bleach in, give it a swish, and then go ahead and fill the cuvette. I could probably even dump that and fill it again, but I'm not going to because I've only done this a couple times. Now check out the absorbance. We recommend that you do quantitative stuff between 0.1 and 1. So there's not the urgency, and that's why in the experiment, okay, I'm close, so I'm going to go ahead and start collecting data right like now. Okay, so in the experiment, and I took this from Jack's and Don Volz's experiment from Chemistry with Vernier, and it says in there, you got to do all this real quick, and you have to be real careful. And then Jack told me, like, I don't know, 6 months ago, he said, Nüs, if you made the concentration really high, then you could mix them, and then you could, take your time and watch the live meter and wait till it gets down to around 1 and then start your data collection. And it's like, really? And sure enough, let's see how the data comes out. I'll let you decide, what you think about the data. But it's a lot less anxious. And I really like that. The other thing is, notice what I did here with the beaker. This is great for, I think, every level, high school, college. Check out what's happening, because this thing's kind of a bit of a black box. And so look at this. It's getting lighter, right? Here's the original. Okay. And now, couple of things your lab techs or you, as if you're the responsible for this. And by the way, I'm watching the meter. When it gets down to around 0.1, I'm going to stop collecting data. You'll need to dilute straight up bleach. It's way too strong. The whole thing will happen in like 10 seconds and you'll get crappy data. You'll get crappy fits and all that kind of stuff. So you got to try it. And it depends on the brand, but don't get sudsy don't get sudsy bleach. Get as plain a bleach as you can find. Sodium hypochlorite, right? The same with this. You need to make up a solution of blue food dye for this experiment, not for Beer's law, for this experiment that has a nice, high 1.7 absorbance, and you'll get better data. And you won't, and you saw what happened. I think I'm going to rewrite the procedure and kind of put on the teacher page, make that stock solution. What you want to do, let me pay attention here so I can stop. I'm going to stop it right about now. If you let it go, it'll drop off. But what happens is when it gets down below zero point 0.1, it's going to drop off like crazy. And then when you go to fit the curves and stuff, it just doesn't look good. And it also just doesn't work. The data doesn't quite work out. We'll see how this one works, but this looks similar to what I did this afternoon. So um, anyway, but see, look at that. Look at the beaker. I just think that's great. Um, so, Melissa, anything I need to know before I go on?
No, you're doing great.
Okay, I just
Yeah.
wanted to check with
Yeah.
everybody. So
Yeah.
is the reaction zero order? No, because it's not linear. Do we want to know for sure? We can fit a curve and we can say, okay, linear, is it linear? I think it's not linear. Okay, so is it first or second order? Well, what I promised you was that we would do this with respect to concentration, not absorbance. So how do you do that? Okay, let's go back and relearn Beer's law a little bit. I'm sorry, I don't like teaching to people that probably know way more about this than I do, but almost every colored solution has a molar absorptivity value. And so if you're not teaching Beer's law, because remember the slope of the line in a Beer's law plot of absorbance versus concentration is the molar absorptivity value, which you could have your students determine that in a previous experiment using blue food color. But what I did was because we had people that were doing the AP Chem one, the sports drink one, and so that's way back when I put this spreadsheet together. And so here are the molar absorptivity values for a lot of dyes. Now, the thing about green, be careful with green, is that the stuff in the grocery store is not green; it's blue and yellow. This is Flynn's. Well, Flynn sells it. I'm sure a lot of people others sell. It doesn't look green. It looks kind of like a bluish color to me. And but anyway, I made this list. I didn't make this list. I stole it from Jack. Jack gave it to me like, I don't know, 10 years ago or something. Well, it had to be more than that because I've been at the office for 10 years. And so there's the molar absorptivity constants for these particular dyes. Um, Food color is blue number one, so 130,000 inverse molar inverse centimeters. And so if you solve Beer's law, absorbance equals or the molar absorptivity constant, the path length, and the concentration. If you solve it for concentration, it's the absorbance divided by the path length, which is 1 centimeter, and the molar absorptivity constant. So what I did for us today to save time, because we only have about 15 minutes left, is I just did that. So here is the formula. Here is the molar absorptivity constant. Here's the inverse, 7.6 times 10 to the minus 6 molar times centimeter. So if I go in, so this question, can you do calculated columns in spectral analysis? And the answer is yes. Click on absorb, the three dots next to absorbance. Let's add a calculated column. The column will be called concentration. And of course, it'll be moles per liter. And now let's do an expression. So what we want, and this is a little bit annoying because I want x over a, and there is no x over a. And so we're going to do the first one. We're going to do a times x raised to the first power. But yeah, well, there's no x over a, so it's like a little bit annoying. But anyway, if I pick this one, I need to make the a parameter that, oops, let me go back. Did I create the column? Let me just triple check. I don't know that I did. I think I tapped outside of it. So let me do it again. I think I didn't do it. So here we go. Concentration. If you tap outside of these windows, it'll take you out. So just be aware of that. Just kind of the peculiarity of the thing. But let me stop talking, get this right. So that it's going to be, what did I say? 7.69 minus 6. You can put scientific notation in. And then if I go over to the right, the exponent's going to be 1. So, so that's good. And so now notice it did it for me. It changed the y-axis to concentration, which is what we wanted. Looks the same because we really just adjusted by a constant. By the way, if I click on the y-axis, I can switch between. I can have them both on the screen, but then they're going to scale weird. So I'm not going to do that. All right, how do we know if this what the order of this reaction is? Well, we teach students that the integrated rate law says that if it's first order, then you'll get, if you plot log of concentration versus um, um, time, it'll come out to be a straight line. So let's test that. So I'll go to 3 dots next to concentration. I'll do the same thing. I'll add a calculated column. This time it's going to be log, but it's going to be the log of the concentration. Okay, and so no units on that. The expression, there it is right there. Okay. By the way, everything I'm showing you now is free. Okay. There are no, on spectral analysis, there's no extra price. By the way, if the students screw up and pick the wrong column, you can always switch to the right column. So if they start the calculation in the wrong column, it's not the end of the world. Okay, so let's take a look at that. Oh, it did it for me. More linear, right? Let's do a little curve fit action here. And so, yeah, that looks not so horrible. And so, wow, look at that. 4 nines correlation. That's kind of linear. Okay. Let's verify that it's not second order. So we'll take the concentration, and the integrated rate law says that that would be the inverse of the concentration. So the inverse of the concentration, if you are a purist, like I don't know how pure I was, but I did 1 over molarity or liters over moles. I did want units because what the AP test does, it'll say, what is the rate constant? And then and if you don't put the units in, the kids don't get credit for it. If they get the right number without the units, they don't get, if it's a 1 point question, they don't get credit for it. So what am I doing? Oh, inverse. Sorry, I'm talking and I'm forgetting. Yeah, here we go. Okay, let's do, what happened? Well, if I click on the y-axis, I can turn on the inverse, turn off that one, and you can see it's not particularly linear. The other nice thing is, I'm going to get rid of this graph because we don't really need it anymore. You can turn it back on if you wanted to. I could look at all 3, right? I could turn on 3 graphs and say, okay, let's look at the 0 order graph on the top, and we'll do it in terms of concentration. Let's look at the first order, so that's going to be log. And down here, I need to turn on time. And let's look at the second order. So I'll turn on inverse. And once again, it doesn't automatically do that for you. And then you can also, I don't think I need these data tables. So click on this box, turn off the data table. I don't need the meter anymore. You can also have all the individual fits. So if you wanted, to have them, I don't really need them because obviously it's this one. So let's do the fit on the middle one, the first order. And so let's turn the fit on. There we go. And there it is. Screen. Sorry about that. I zoom my screen out so you can't see everything quite as nicely. But we want the slope, right? So the slope is the rate constant, and for first order, it'll be inverse seconds, right? And so they can write their rate expression. Where is my PowerPoint? There it is. And so they can write their, oops, I jumped ahead here. So they can write their, oh, where is it? Okay. Anyway, I don't know where I put the slide. I kind of got lost here. But I did have a slide at one point that said, the rate equals, you know, in this case, that value for the slope times the concentration raised to the first power. So that's something that a lot of people want to be able to do. And of course, it goes back to that whole thing at the beginning of the AP tests where they have all these different graphs and which one is the one that represents the order of this reaction, which, it could be in terms of more than one reactant. I mean, do you want to do it against concentration of bleach. That's a little hard, I will tell you, because the bleach is so much more concentrated. So we call this kind of a pseudo first order because we're not taking into account the bleach because it's way, way concentrated. But I've had people do it. I don't know. I don't know what kind of results they get. I mean, is it first order? I have yet to find a single reactant that's not first order. Reactions overall, if it's first order, then overall the reaction would be second order. Anyway, I want to do one more thing. Yeah, we have time. So I'm talking fast. Melissa, how's it going?
It's going good. I'm answering some questions in chat, so
Okay.
you're doing great.
Okay. So the other thing was um, I wrote the experiment to match the level of your students. So you can decide not to do the rate stuff if you're doing a lower level chemistry class. You can just look at that initial graph. Let's go back to it. And we can just put on one graph. Isn't graphical now, or they're both the same, but aren't they really nice? So this is the just concentration. Now, how do you find the half-life? Well, what was the absorbance near the beginning? You can take this thing and drag it all the way to 0 seconds, and the concentration, oh, dang it. We've talked to the, it's in scientific notation, and it's like, wait a minute, it's not showing me here. So I don't know if I can change. Let me go to the table and see if I can change the, why is this not working? There we go. Let me see if I can change the way it's showing concentration because it's in scientific notation, it's showing 0. Um, all zeros because of it's not scientific notation actually, this is decimal notation. But if I go to the column options, I can change it to scientific notation. Let's try that first and see if that gives me a value on that flag before we fool around with the number of significant figures and stuff. But let's see, is it in it's in scientific notation? Yep. And so theoretically, the value should be something dot something something times 10 to the something. And they're not. Oh, there we go. There we go. Okay, so that's working. Let's go back to 0. 7.6 times 10 to the minus 6 molar. Okay. And then, okay, now what's half-life? Well, this is a whole discussion with your students, right? Half-life is when half of the chemical in this case has been expended or changed its state, something. So 7.6 times 10 to the minus 6. So I'm looking for the time when that drops to 3.8, right? So let's do that. So for a class that might have, um, by the way, to make this more work smoother, if I fit a curve to that, and I'll leave that to you to decide if you want to mess with that. Um, I didn't fit a curve. This is just, let me show you. If I go to the things, it's taking the points and it's connecting them with lines, and it's just jumping from point to point. That's why it looks a little jumpy. If you were to try to fit a curve to that, and I guess this one will be a logarithmic fit, it doesn't really matter if it's a perfect fit because well, so if we do apply curve fit and we do a logarithmic fit, so we'll do natural log. And that's not great. Let's see if I can find something that fits the data. Yeah, that fits the data better. Because what'll happen is now when you go and you try to interpolate, oh, I got to turn interpolate on. Here it is. Then it will do between the points. So your call. I'll leave it to you. What happened to my scientific notation? Kind of went away. Interesting. With the fit, it went away. But the that will make it so that you can go between the points. So let me see if I can play with that. I'm gonna instead of scientific, I'm just gonna make it decimal. Oh yeah, look, it went back to decimal. Isn't that interesting? I'll make a bunch of decimals. So I'll make 7 or something. And so there, now we'll have a bunch of numbers. And so up at the top, it was 7.6-ish, or so that was 76. And so now we're going to look for 38. So we'll go down to 38. And now it's going between the points, so it's a little smoother. Kind of your call with your students if you want to mess with that. But they're pretty close right there. So 43 seconds for the first value. And then what you can do is, okay, this was 38. So it should be another half-life would be half of this, so that's going to be 19. So we keep going. And we're running out of data, but there. So now that was 43 seconds. Now it's 86 seconds. Hey, that's not horrible. That's pretty consistent. And then 19, half of that is, what is half of 19? 8.5. And so we go down and we might be able to squeeze one more into the data set here. And so that's one way to manually find the the half-life. And on the experiment, I had a table and the kids record these values and do an average value. So that's one way to do it. The other way to do it is the right way. And that is to use the half-life for a first order reaction. The half-life is, if you do all the manipulations of the first order, I didn't put it here, but I put it in the experiment. I didn't put it here because it was becoming a lot of stuff. I put the first order, the log at the initial log and all the stuff in between, so you can solve for K, or actually solve for T at half of the time. And because at the initial time, T is 0, and then you plug in for the final T, T1 half, and you solve the equation for T1 half. And this is what you get. And so what's K? It's the slope of the line. So if you go to your experiment and you change it to the first order plot, turn off the that one. That's not it. The log, sorry. And now, the slope, and this is, I don't want natural log fit. Let's do a linear fit. And so that slope, negative point, whatever, that's the value of K. And then you can have the kids predict, what the concentration will be at different, pardon me, that's the value of K. So you can do the half-life for the whole thing. So let me get back to where's the PowerPoint? There it is. And stop for a second. We have less than 5 minutes. Anything anyone has to know the answer to?
No, we've just been talking back and forth about some kind of different options. People are really interested in the fact that this is, getting away from crystal violet, which is really toxic. And I was sharing our green chem resources in the chat. So I was just looking for that link, but no other
You haven't gotten
questions.
any, I don't know if I want to say approval. So when people ask about green chem, if we have an experiment, we're happy to share it. And like I said, we've been doing webinars with them. So if you look on our list of webinars, you'll find you won't find the acid-base titration, but you will find the conductivity titration. And those, once again, the acid-base titration is ammonia and vinegar. And so what you end up doing is you standardize which one do you standardize, Melissa? My brain went blank. You standardize one of them, and then you use it for the conductivity titration, um, and um, and so it's those two experiments kind of go together. You're standardizing a substance, and I apologize, my brain is still stuck on this experiment. And then you take those results and you use them for experiment number two. And that's, if you're familiar with our books, that's experiments 5 and 6 in advanced chemistry. Um, Now, this experiment that I just did, like I said earlier, you can do this with a colorimeter, and if when you download the files, you can get the files for doing it with a colorimeter, and you can watch a recording. It's very similar to what we just did. So I encourage you, those of you that don't have spectrophotometers, do it. The spectrophotometer is kind of an amazing device, and I was a little bit disappointed that Vernier had never written a flame test experiment. And this thing can do absorbance, percent T, it can do emission spectra, and it can do fluorescence spectra. It's only got 2 excitation wavelengths, but still, if you're teaching how fluorescence works, so in the forensics book, there's an experiment called Secret Message. That one is a fluorescence experiment. There's also one called metal poisoning, and that's a flame test experiment. So you can get a lot of use out of this thing, which you may or may not have realized you could. So that's the difference. This thing, it does actually it does percent T, and then our software converts that to absorbance. So that's pretty much it. And it's 4 wavelengths. So you can do a lot. I used to build these out of blocks of wood back in the 80s and the 90s. These are much nicer, as you can imagine. But my Blocktronic still works. I tried it the other day, and boy, I was getting data. All right, let's go back since we're running very short on time. Dylan, are you still with us?
I
Dylan
sure am.
has a cold, so I might have to wake her up. So Dylan, we are giving away, I understand, a Go Direct colorimeter. Um, do you know who's getting it?
Absolutely. So I put everyone's names into a random name generator, and I know who is winning our Go Direct Colorimeter. Our winner today is Christy W. So congratulations, Christy. Please keep an eye out for an email from me. It'll be an @Vernier email address. So I just need to get some information from you, and then we will send you your Go Direct Colorimeter. Congratulations.
And finally, I want to remind folks, you're going to get a survey from Dylan, and there's going to be some things in there like, what would you like to see? And so absolutely, please let us know. Melissa and I both do these all the time, and I love doing them, as you might be able to tell. The other thing is, if you have trouble, don't wait. Oh my, I feel so bad when I talk to I've been trying this for 3 days and I can't get it to work. Please call us, write to us, chat with us. Vernier.com, you can do a live chat. And the only thing you need to realize is a good hunk of you are further east than we are. We're almost as far west as you can go near Portland, Oregon. So if you want to talk to us at your time, 8 a.m., that's not going to happen because that's 5 a.m. for us. But be aware of that and send us a message or, something. And we would love to talk with you and work through any issues that you have. Melissa, anything else before we sign off?
I don't think so. Thanks everyone for coming. See you next time.
Yeah.
Bye, all.